You're going to be the button presser on this board?
Apparently.
Standing by who? That's middle button's the laser, and then it's left right.
Yeah, it's not working.
Naturally.
Yeah, cross. Clicker's not working. No, it's on. I'm just not sure what's going on.
When we ground, you're not plugged into the power.
Real fast intro. You
Okay,
guys can
and
step
then
up there
Stephen
with me
will
if you want.
kick us off.
So I'm going to do a really fast intro, and then you guys can
You snuck up on me.
Good evening. That seems a little bit loud. Can we get it turned down a tad? I don't want to blow people's eardrums out. There, that's better? Good? Yeah? Okay. Welcome to Steam Cafe. Steam Cafe is a partnership with Haycamp Brewing and South Dakota Public Broadcasting. So we thank them for their support. We thank you guys for coming tonight, and thank you to those of you who might be attending online. We are broadcasting on Zoom, as we always do. And we will do a Q&A at the very end. So if you have questions at the end, raise your hand. We'll call on you. If you are attending online and you have questions, you can type your question into either the chat box or the Q&A box, and we will make sure that those get answered live and in person. So without further ado, our presenters tonight are the South Dakota Mines bladesmithing team. This is a different team than in 2018, but the bladesmithing team in 2018 was actually the very first Steam Cafe presentation ever. So this is part two with a new team. So we're excited to have them back.
Hello, everyone. I'm Stephen Gebes, sophomore studying metallurgical engineering at SD Mines and leader of the bladesmithing team for the 2026 project.
My name is Nathan Staley. I'm a PhD student at South Dakota School of Mines, and I'm running the metallurgy side of things for this coming project.
I'm Brianna Hoff. Is that on? I'm Brianna Hoff, and I'm a master's student at South Dakota Mines, and I helped a lot with the last bladesmithing project.
My name is Cora Gehrke. I am a sophomore in the metallurgical engineering department, and I am the executive officer for the 2026 team.
To begin with, I want to speak a little bit about metallurgical engineering. Thank you. To begin with, I want to speak a little bit about metallurgical engineering. Metallurgical engineering is the study of materials, specifically of metals. And we have a very unique program at SD Mines for our holistic approach to metallurgy. But I would say what's really special about us is that we are one of about 10 in the entire nation. Now, metallurgical engineering has, you could say, two directions. One of them is the forward direction, which includes metal extraction, production, processing, and testing for performance. And the backward direction would be the recycling and sustainability portion. We incorporate both of those at SD Mines and learn quite a bit. Of great interest is the fact that metallurgy is one of the most important and fundamental studies for the upkeeping of our society, since we provide the raw materials, the raw metals, for every other profession in the world. The TMS Bladesmithing Competition is a biannual international competition hosted by the Minerals, Metals, and Materials Society. It started in 2015 to broaden the public's understanding of material science and to provide a competitive spirit to the students in metallurgy. You can consider this to be a lot like Forged in Fire, just a lot more technical, since it involves a technical report, a memo, and a video describing everything. Since its inception in 2015, I can proudly say that SD Mines has submitted the blade for every competition and has taken home many notable prizes. The inspiration behind our 2024 blade is a sword found at the Sutton Hoo burial site on the eastmost side of Great Britain, specifically the East Suffolk region. Now, this sword was made in the early 600s, likely, a period called the Migration Period, which marked a great turning in the time due to the invasion and incoming populations of Saxon and other such peoples. It was a great time of political upheaval and of technological improvements, major technological improvements. This sword was, without a doubt, wielded by a king to display his majesty and glory to all the barbarians who would come. Now, this sword is significant for a multitude of reasons, one of which would be that this is one of the most ornate swords found from the time period. Another reason would be the fact of its technological advancement, including, and most significantly for our purposes, a pattern-welded blade, a gold cast pommel, and garnet set in cloisonne.
Now, for this project, one of the big goals was to produce the iron and steel from local materials. Now, local ore is collected from the Black Hills, apparently from a bog iron deposit. I was not part of the collection team here, west of Rochford. And smelting was carried out by combining crushed iron ore with carbon and heating that to a very high temperature. Now, when you do this, the chemistry of the melt changes slightly, where it now becomes more favorable for the oxygen from the iron ore, which is primarily iron oxide, we'll get to the rest of that in a minute, to basically combine with the carbon, form carbon monoxide or carbon dioxide, and leave behind purified iron. Well, purified iron. As we can see with that block down in the lower left-hand corner, or right-hand for you guys, sorry, you're left with a spongy iron mass that then has to be consolidated through hammering. So you'll have one guy sitting there with a pair of tongs, long pair of tongs, holding this very hot piece of metal, and then the other guys are whacking on it with a hammer for a long period of time. Now, this hammering process not only consolidates the iron, but also drives out certain impurities that are left over due to it being a mineral deposit. And those impurities can lead to mechanical problems later, which we had to mitigate in some aspects by pattern welding. Now, the pattern welding also came into play due to that being used in the original inspiration blade. The local iron was combined into a serpentine pattern with 1018 steel, which is a lower carbon steel, allowing it to better bind to the low carbon iron produced, which formed one side of the blade. And then the second side of the blade was formed from a 1084 and a 15N20. Now, 15N20 is interesting because it has a higher nickel content than a lot of basic high carbon steels, allowing for the pattern to become more visible when we etch it. These two were flattened, formed into the two sides of the blade, the flats of the blade, and then a 1075 and 1095 edge was added. For those of you who don't know, 1075 and 1095 are two very common blade steels that can be hardened and then tempered into a significantly more viable edge compared to a 1018 or the iron that we produce for the serpentine pattern. This gets us into the pattern welding. This is where you're layering those various steel alloys that I mentioned. We're not just melting them together, we actually stack them, layer them, cut, fold, hammer into the pattern that we want, and then forge wheel the pieces together into the blade. So you'll start out with a block, hammer it out into a flat, combine those flats, forge weld them together, add the edge, and then shape that into the final blade length that you see there, which is then polished, etched, and, well, we didn't get around to sharpening it. And when you do etch it, which is generally in an acid etch, you end up with the pattern on the far right side where we have the serpentine twist, and then that twisted, almost wood-like bark layer.
Okay, so like Nathan just talked about the. Can you hear me now? Okay, testing. Cool. Good enough? All right, so like Nathan just talked about, the forging is the process of getting the material to the shape we want, but the heat treatment is really our opportunity to tailor the properties to those that would be good for our specific application, in this case, a blade. So the two heat treatment strengthening mechanisms we used for this is grain refinement and martensitic transformation. Grain refinement is just taking the individual metal crystals, pictured here, and nucleating more of them so that they're more and smaller. And that produces a material that's stronger. And then the martensitic transformation over there, that's actually something that's pretty special to steel. And so we're actually changing the arrangement of atoms to get a structure that is more suitable for the properties we want. So up here is our heat treatment schedule. This is basically like a recipe that we put our material through. So you can see we start out at room temperature. This is after it's been forged. And we're going to heat it up, cool it down, slowly cool it down, do that twice. That's producing our grain refinement here. Every time we go above this line, we're getting new grains growing, and so they're smaller. The other thing that happens when we go above this line is we're actually transforming this ferrite, this BCC phase, to this austenitic phase. And as you can see here, more carbon is able to solubilize into the microstructure in this austenite phase. So when we get it up here and then we're going to quench it, so that's just a really fast cool, what happens is this material actually wants to go back to this structure when it comes back down to this temperature, but because we cool it so quickly, we trap it in this intermediate phase called martensite, and you can see that a lot of the carbon is still there. And that produces material that's both really strong, but it's strong because it's really stressed, and all this extra carbon adds a lot of stress to the material. So after the austenitizing step, we do a double temper, which is where we just heat it to a lower temperature and hold it there, and that allows some of the stress to be relieved, but we're not allowing it to actually transform phase again. So the nice thing about heat treatment, or something you have to work around depending on how you look at it, is that the materials will all respond differently based on their chemistry. And so In our case, that's going to be helpful for us. We can design our blade around the different materials we're using, because we're using the iron, so we'll put that at the center. The iron doesn't have all the carbon in it, so it's not going to form that really strong and brittle phase. And on the other hand, our commercial steels will put that on the edge, like Nathan was talking about. The carbon gets trapped and produces a strong material. Okay, so after we do this, it's kind of like baking a cake. You don't really know how successful it was until you cut it open, and then most importantly, taste it. So for us, that looks like cutting the metal open, looking at it with a microscope, and then also testing its properties. So let's talk about this first. We can see that the grains did get a lot smaller. So like this is a whole grain here. And as we go through the heat treatment process, they get a lot smaller. Additionally, we go from like this pearlitic ferrite structure to this martensitic structure over here. So the metallography shows that our heat treatment was successful. And then we can talk about the numbers, the mechanical properties that we tested. So we did hardness testing, tensile testing, and impact toughness testing. Hardness is you just make an indent in the material and then see how far that goes, and you can test the hardness like that. So you can see with our iron and serpent, those ones that we smelted, they're very soft compared to the commercial steels. We went from about 100 Vickers to 700 Vickers. And then 700 Vickers, that's stronger than most knives would be. 100 is closer to like a structural steel that needs to be tougher. So down here we have our tensile curves. What happens in this test is we just have the material cut out and we pull it apart. And so as we're loading it, we're measuring the stress, or we're calculating the stress, and then we measure the strain, so how much the material is just stretching apart. You can see with these blue curves here, these are our commercial steel, the twist. And as you load it, it's actually moving very little. And then it does start to move up here, and where these lines end, that's actually where the material fails. So we have a fracture up here. And then for our iron piece here, it can't take as much of a load for sure, but it actually stretches a lot more. So that's an indication that it's a lot tougher. And if we look at impact toughness, that's actually where we just take a bar of the material and we swing a big hammer at it basically. And we measure how much energy is taken out of that swing from the material. So you can see that the serpent, it was 112 foot-pounds, and compared that to the twist and edge, which are about 10. So it's an order of magnitude higher toughness for our iron samples.
All right, before I start, can you guys hear me all right? Yeah. Sweet. So this is now getting into the arts and crafts section. If you guys remember on the original sword, you saw that cloisonné garnet pommel. This is kind of the process for forming that pommel. It starts with creating the pommel itself. The leader in 2024, Chris Mercado, designed this in the Blender software, and then it was 3D printed with wax resin. This allows us to put it into an investment casting and basically burn it out. You'll commonly see this in the jewelry industry. They do this process a lot as well. And then afterwards, we casted it in bronze. The historical one was cast in gold, but we were kind of on a budget, so bronze had to work. Yep. So then this was the final results. Also doing the wax resin allows us to get this detail on the side here without too much post-processing. And then because we wanted to stay true and have that gold design, we decided to research how to do electroplating. This allows us to use electricity to coat the bronze in the gold. So for that, we learned that aqua regia is one of the most common ways that you can dissolve gold to allow it to electroplate. It kind of looks like brushing on, but there's like a hum in the background because you're using electricity, of course. And it creates kind of this gold pattern. The gold was provided by Dr. Carlson, who got it from the late Dr. Howard. And it doesn't look like it'd be that different in color, but this was before we electroplated it, and this was after. You can see a drastic difference even there. And once that was done, we moved on to the garnets. So cloisonne is the method we used. It's a lot like stained glass, but it's reverse, where you make the outside pattern before you cut the pieces. And so having the pommel cast out already, we were able to start working on the garnets. We got some from the Black Hills, but because they're smaller and more brittle, we had to supplement it with some from Idaho and India. This process took, if we were to work it straight, it probably took 2.5, 3 weeks to fully complete all of the garnets. But in the end, we were able to make all the pieces and peen the edges, which is where you hammer the edges. That way it curls over the garnets and keeps them in place rather than using glue or something. So that's what the finished pommel looked like. And after all this work and time, we were able to place first place and win the Wadsworth Shirley Grand Prize Award for the 2024 competition. It was great because we got to compete with international teams and see how they did their stuff as well. And up next, we're gonna have a video playing for you guys. This is the video that Gebes mentioned, with which we had to turn in for the competition.
Gotta get the button.
What you're looking for?
The one to the left? Oh, that's the YouTube. Okay, I thought it was the middle. It's like a full screen video. Okay.
Our team has set out to create its most ambitious sword yet, one with both historical and artistic finesse, as well as high metallurgical performance. Modeled from the 6th century Sutton Hoo European sword, and without the help of an artisan, this project would involve double-sided pattern welding, ornate garnet fastening for cloisonne, and gold plating. Additionally, the team desired to collect and smelt its own iron ore from the Black Hills of South Dakota. Once the ore was collected, it was roasted, crushed, and fed into the bloomery with charcoal to begin smelting. The reaction was controlled by adjusting airflow through the tweers, and slag was periodically tapped to prevent them from fogging. Once the reduction reaction was complete, the bloomery was dismantled to remove the bloom. The bloom was repeatedly folded to create a billet with fewer impurities. Unfortunately, the forging characteristics remained poor, and X-ray fluorescence, metallography, and energy dispersive spectroscopy revealed the presence of high residual sulfur and impurities that made the billet unsuitable as a primary blade material. Despite this, the team was proud of the effort put into the iron's production and decided to incorporate it at the blade center. The center serpent bar was made by forge welding the iron with 1018 steel. High carbon 1084 and 15N20 steels were forge welded together into 2 bars and twisted. These were then forge welded to the sides of the serpent bar, creating a new billet. Next, scallops were cut out of this billet and it was flattened to create the wavy serpent effect.
6 more twist bars were created with 1084 and 15N20 steels. 2 were welded to the billet's edges to create the front face of the blade. The remaining 4 were welded to the back to create the back face. In this way, a double-sided pattern weld was accomplished. A hard edge bar wrap made of 1075 and 1095 was forge welded to the blade core, creating a rough blade billet. Next, the blade was forged to shape and thickness, beveled, fullered, and ground to a rough finish. After normalization, the blade was austenitized and oil quenched. A double temper completed the heat treatment. The blade was finished with hand sanding and etching in ferric chloride. Metallography and hardness, pencil, and Sharpie tests were performed on material taken from the various bars. Testing on the final heat-treated material showed high hardness edge and twist material and tough serpent material. 3D modeled pommel and plates were printed, molded, and cast in bronze for sections of the handle. After the plates were cast, they were cleaned, polished, and filed. Following this, they were used to enclose a layer of horn and were riveted to make the upper and lower guards. These guard plates, as well as the pommel and the waffle pattern foils, were gold-plated with a solution formulated by the team. Ebony and antler spacers were cut and shaped to make the handle. The guard plates and the handle spacers were then assembled, epoxied, and secured by cleaning the tank. For decoration of the pommel, Black Hills garnets found by the team, along with some from India, were selected. These garnets were ground to slabs and polished. Each garnet slab and a gold-plated waffle foil was then cut to fit the cells of the pommel. Once the pieces were inserted, the bronze walls were peened using a punch and hammer. The pommel was secured, completing the sword.
That's cool. All right, if any of you had difficulty hearing that at all, you can find the video on YouTube. All right, to conclude this evening's talk, I want to go over some of the new stuff that we've been working on for the upcoming competition in 2026. Next year, we're going to be making ourselves a shamshir, which is a Persian blade, typical to the 15th century onwards. Our inspiration behind our design was an 18th century blade used as a ceremonial sword for the coronation of a Turkish sultan. This is a very luxurious blade, very expensive, possibly one of the most expensive ever made. And it displays some of the characteristics and some technologies which SD Mines has never attempted before, including gem setting, lapidary work, and most importantly, root steel. Root steel, or as I like to call it, true Damascus, is best defined as an ultra-high carbon steel with an inherent pattern in it, which is made in a crucible. That is a container used to hold the molten metal in which the steel is slowly cooled in. The real trick behind roots is having a significant portion of it being a high percentage of alloying elements such as vanadium, chromium, and nickel. These alloying elements cause the segregation and collection of carbides. More on that in a second. And as you can see here, it makes quite lovely patterns. Interesting part about roots is that it was discovered by accident. Prior to modern metallurgy technology, the ancients didn't exactly know what was going on in steel with all the alloying elements. And so they would just dig up whatever iron they would find, throw it into an oven and see what would happen. In places in the Near East, such as Syria, going onwards towards India, they found deposits which included high contents of vanadium. This accidental discovery led to a technology which is best understood to be the first super steel of the world, since the special properties were basically legendary, including the ability to hold a hard edge when no other swords could and still retain a significant amount of ductility. An example of wood steel would be what's shown here on the left. The banding here shown is caused by the varying concentration of carbides, which, as I promised earlier, are the collections of carbon atoms attached to the elemental metals, such as the vanadium, the nickel, and such like that. These alloying elements collect the carbides, and due to their significant presence, they cause this banding structure to occur when forged out, due to the swirling, you could say, the swirly nature of the crucible once it's fully solidified. It should be noted that this is an entirely separate process than what was used in the TMS 2024 blade, which is pattern welding as shown here. The distinction is can typically be understood by seeing that this pattern is more or less chaotic, whereas this is very clean, almost predictable really, very clean lines. Again, woods, not woods.
All right, so this is where my work comes in. We are using a historically informed composition. It is not precisely what they would have used in history. We're using very pure elements compared to the ores that they had access to, as in we are literally using pure vanadium particles in some aspects, and then iron, manganese, iron chromium, and then pure nickel to add in the amount. You can think of Woots as effectively a microalloyed tool steel. Compared to modern steels, it's not magic. This isn't some sort of super steel anymore. It's mechanically comparable to something like 1095 that we have today. That's simply because our technology has advanced to the point that we have steels that arguably aren't really steel. But back to the project at hand, we melt these pucks, which we start with primarily iron powder, add in some carbon alloying elements, in the crucible, as Stephen mentioned, with a layer to prevent oxidization. If oxygen gets in there, it pulls all the alloying elements out, all the carbon out, you end up with something that's kind of weird wrought iron. This is our first successful puck. I'm very proud of it. You can see the patterning on the outside, which honestly, that was just so cool when I opened it up and saw that. Anyway, not gonna nerd out too much here. And on the inside, you can see the dendritic pattern that's formed by the perlite. If you were to look at it under the microscope, that perlite phase that's been mentioned is effectively a lamellar ferrite carbide pattern. And then on the outside of that, you will see larger sections of carbide. Now, we want that. I mean, if you were to see that in a modern steel, not great. We want that here because it will produce that chaotic pattern once we forge it. And we have to control the forging process very precisely. Our forge master is not here right now, so he could explain exactly what he did a little bit better than I can. However, we want to produce this. How we produce this, sorry, got off on a tangent there, is we induction melt it in the crucible. That is, how do I put this, a concerning process, because the crucibles we are using get to the point of almost breaking down when the steel starts to melt. We have to hold it at the molten temperature long enough for everything to dissolve into the iron, at which point we run it across the foundry into that propane furnace right here and let it fire for a couple of hours, which allows us to produce this more or less as cast microstructure. And we're working on getting this to replicate successfully. You can see the examples in the back. We have crucible, some materials that this is a lot smaller than you would think. It's probably about the size of the end of my thumb, because we're running 200-gram batches here. Anyway, yeah, Stephen, are you running the acknowledgements? Yeah. Anyway, this is the end of my research here. It's ongoing, and we'll update you soon. We'd like to acknowledge the team members that are not here with us right now, thanks to them graduating. Chris Mercado, Anthony, aka Tony Romero, Tyler Renarts, Cole Ledman, Thaddeus Malsalam, Svierding, and Isaac Johnston. These guys did a ton of work on here. I'd also like to thank Stephen, Brianna, and Cora for doing the majority of the work on this blade, and especially the majority of the work on the 2026 blade. Stephen here is sort of our ringleader and mastermind, and he's somehow convinced us all to do this cool Shamshir project. And we'd also like to thank Dr. Cross and Dr. West here in the audience for supporting all of our work on this project. If you have any questions, please ask. We love answering them. Thank you. Yes.
When you go to this competition, what exactly are you judged on?
We are judged on several criteria. Primarily, I would have to say, is the metallurgical significance. Why is the blade special from a metal standpoint? What did you do that sets you different? Other than that, another important factor would be the beauty aspect. And this is very appropriate for the STEAM Cafe because this combines both the science of metallurgy with the art side of things. And so we're also very much judged on the art side of things, but primarily the technical stuff.
Yes.
How many human hours did it take to make the world?
It's,
Immeasurable. I don't know.
A lot.
to put it into perspective, it's a 2-year process, and we got down to the last few hours.
How many hours per week would
If
you spend on?
me and Cora kind of ended up late into the project, right, Cora? You know, and so I wasn't very familiar from the very beginning. But if we're counting research, definitely several hundred hours.
Yeah, hundreds of hours they spent on this. It was almost too much.
It was quite the obsession.
For reference, the little steel puck that we've been working on, that puck in and of itself is probably about 6 hours of work to produce the puck, 6 to 7, depending on how long we fire it. And then to get it cut to where we can polish it and run testing, that's another 2. It takes a while. And then the forging process that the rest of the team is working on, I don't know how long they've spent on it, but it's a lot. So,
And that's without the research on
and
top of
that's
that.
just for one person, by the way. That's not counting the other man hours. So we're talking probably 20 to 30 man hours.
Suffice to say, that was a big project, and this is going to be an even bigger project.
Yeah, because we have to make one, that's 200 grams. We have to make a 2,000 gram one of those.
It's going to be fun. Do we have any
And
other
terrifying.
questions? Yes.
In the video, something had a scabbard to it. Do you actually have a scabbard that goes with it?
That was an example blade that somebody else made, mimicking the same inspiration sword. I don't believe we got around to making a scabbard that year.
If we get really ambitious, maybe we'll make one, because it would look really cool in the display case, but as of yet, we don't have one.
We ran out of time, is what happened.
We really did.
Yeah.
Last 2 weeks, we were pretty much working all the time on this project, so.
Yeah, they were texting at like 11 o'clock at night. I was, I think, asleep when they were like, "We're finally done."
It was close, for sure. Any more questions?
How is this project, this activity, going to help you in your professional career?
So this allows multiple aspects. For me personally, I'm a PhD student. I'm working on a steel-related project, and it is the carbide development specifically ties in to, not directly, but it's definitely the reading and getting that large-scale understanding of all the materials probably that go into it. Historically, where does our industry come from? With, as we mentioned, the vanadium and the alloying elements, each of those plays a different role in modern steels. So take, for example, manganese. If you up the manganese content of a steel, it starts behaving really weirdly. You know, with different crystal structures forming. When you modify it, you can see, take, for example, TWIP steels, twinning-induced plasticity. The steel doesn't, when you deform it, you start seeing these twins, or basically the crystal structure reflecting itself in the microstructure. Yeah. With the vanadium carbides come out of solution very early. And so if you're trying to get higher heat resistance in your steel, say you want to hot work things with a tool steel, you will add things like vanadium and chromium to allow the working temperature of the steel to increase. Not to mention the sort of instinctual knowledge you grasp when you start working with metals by hand. You understand how they deform, which can then, if you're working in industry, can help you understand, okay, if I'm doing an industrial forging process, how is this metal going to react? Is there anything I have to watch out for? With the jewelry aspects, you start getting non-ferrous metals like bronze, gold. Those behave very differently than steel. Steel's a lot tougher. Those are a lot more ductile. They chemically behave differently. And so all of these different aspects really inform every student's understanding of metallurgy as a broad field, and can even expose them to other fields such as geology, gemology, different art fields. You know, we had 3 or 4 different art forms present in that sort alone. Woodworking, 3 different types of metalworking, gem setting. This sword will introduce everybody to everything from literal gem setting, we're planning on doing that, to lapidary work, multiple forms of metallurgy, the chemistry involved in it. It exposes you to every facet of the industry, and industries, plural, actually.
And on a less technical aspect, it makes you appreciate the history of the sword of the metallurgy better, because without this project, I know I probably wouldn't be looking out for historical swords and seeing the kind of beauty that they have and the amount of effort and work that they put into it, the amount of appreciation that goes into whoever had to do that poor pommel back in the day. Kudos to them.
Yes.
Yes.
On the subject of history, you provide some historical context as 2024 sword. To you, what are some of the most interesting differences between your method for creating this sword and the methods that would have been used to create it?
We have access to a lot more tools and a lot higher technology. Our steels, especially the steel that is commercially produced, is a lot more pure. We know what's in it, we know how it behaves, we can forge it very easily. All the steels we used are very, very common knife steels. Back in the day, if you were producing pattern welding, it's pretty much magic. There's a reason that blacksmiths, especially in England and Europe, were considered to be functionally wizards. There was this thing where you couldn't break an oath sworn over a blacksmith's anvil. And that's because these were men that had developed a knowledge, partially passed down from whoever their mentor was, partially from hundreds or thousands of hours of personal experience. We're doing this as students that can read manuals and the internet, and we do have a lot of experience with forging, but not nearly to the extent of blacksmiths that would produce that blade. Not to mention the goldsmithing, the fact that we're using modern lapidary equipment. We have diamond-coated discs that can polish those garnets and slice them. They would have had to been doing that with sand, and very limited, far more time-consuming than what we would have had. There's a reason that the sword was buried with a king. It's because only a king could afford something this complex. Not to mention the time spent collecting garnets. We ordered garnets off of the internet from India for a large chunk of those. They would have been digging them out of the Thames and trading for them. The gold would have been brought potentially from other countries, and you had the purification process with that. The amount of time that the ancient artisans would have put into this is, I mean, we talk about hundreds of man hours, it would have been thousands or tens of thousands of man hours with potentially dozens of master craftsmen producing that.
Does that answer your question well? Very nice. Yes, Matt.
So what you're saying is you're still wizards, it's just you have a different type of stride. And very, very effective hits.
I think we're more sorcerers than wizards. We had to read a whole lot more, so.
You're making with the law.
Yeah, there you go.
Hopefully more ethical than Disney, but
Any final questions?
For all those that are here, we do have the sword on the back table there, as well as some of the example pieces from the 2026 project we have so far. So if you'd like, please look at those.
For those who are not here, you can come visit SD Mines and come see it in our display case, devoted to swords.
And we have a lot more there too.
There we go. Thank you again for coming tonight. We do this every third Tuesday. So next month, April is National Poetry Month. So we're going to have two of our faculty from Humanities, Arts, and Social Sciences discussing poetry and the science behind poetry. So again, STEAM. So hope to see you next month. I believe the third Tuesday is April 15th, if I recall correctly, but right here, 6 p.m., third Tuesday. Thank you.